Hello, my name is Andrew, and this is my magnetic field of a bar magnet lab for Physics 2212. For this lab, I use a bar magnet and an app on my phone that displayed the magnitude of a magnetic field in order to measure the magnetic field at different distances on a meter stick. Then I use a computational model to visualize the magnet's magnetic field, and I determine the effect distance has on the magnitude of a magnetic field and the magnetic moment. N equals negative 2.8049, and the magnetic moment was 3.69 amperes meter squared. The formulas that I used were the magnetic field of a bar magnet, the magnitude of a magnetic field of a dipole on axis, the linearization formula, Biot-Savar's law, which is here, and another version of the law here, which uses the magnetic moment. And some of the concepts that I use for this lab is that a bar magnet acts as a dipole where the magnetic field goes towards the South Pole, as we can see in this picture here. Some of the assumptions I made for this lab is that the bar magnet is treated as a magnetic dipole, and the Earth and bar magnet are the only magnetic fields acting on the system. The system was the magnetometer in the phone, and the surroundings were the bar magnet's magnetic field and the Earth's magnetic field. And in this diagram over here, we can see where the bar magnet is in comparison to the phone. So for the first part of the experiment, I moved the phone on axis along the meter stick to determine where the magnetic meter is located in the phone. I also rotated the phone so the x component from the Earth's magnetic field would be 0. I found that the magnitude of the magnetic field decreases when the magnitude of r increases, and the phone is further away from the magnet. This graph shows the log graph of the magnetic field and the distance, and shows how when the distance increases, the magnetic field decreases. For the second part of the experiment, I slid the phone to d perp, which is where B net equal to 100 microteslas. Here I record the y component of Earth's field and determine the x, y, z components of the magnetic field when the magnetometer is located d perp on the x and y axis. I also determine d and the corrected by for Earth's field. And here you can see all of that data recorded. Two observations I made were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So in order to find n, I had to look at the graph and use Excel to find the slope of this line. N is equal to the slope, which is negative 2.8049. So then using what we just learned from the last slide, we can determine the magnetic dipole moment. So we know that ln k is equal to the intercept, which is negative 13.831. Now that we know what k is, we can determine what r is by using the value we got for the bar magnet's magnetic field, n, which was the slope, and put it into this equation, isolating r, and find that r is 0.228. And then using the equations for the magnetic field of a bar magnet and the dipole on axis, which are the same in this scenario, we can set these equations equal to each other and isolate the magnetic moment. And when we do that and plug in all the values, we find that the magnetic moment is equal to 3.69 amperes meters squared. For the computational model, I first defined the field for a dipole by defining the magnitude of r and r hat, and then using this equation, which was this equation, just put into code. And once I had that function, I used it in order to create magnetic fields at each of these points, and I created arrows to represent these points. Some of these points are along the axis and some are perpendicular. I set d perp equal to 0.313, which we found from the observed data, and then created one last point, which was 45 degrees to the axis. And that code gave us this model, and we can see the purple arrow is 45 degrees from the axis, the orange arrows are the magnetic field perpendicular to the axis, the blue are the magnetic field on axis, and the size of the arrows represent the magnitude. So the results for this is that the magnetic field for the observed data was 6.233 times 10 to the negative fifth teslas, while the computational model found that it was 6.327 times 10 to the negative 6 teslas, which is a good bit smaller. This difference is due to the sources of error, which were the magnetometer was not completely accurate and varied a lot when we were trying to determine the magnetic field. The magnetic field from other devices in the area weren't accounted for. The phone may not have perfectly been rotated to make the x component of Earth's magnetic field 0, and there may have been some mismeasurements of the distance or where the magnetometer was located in the phone. So what if I hadn't oriented the experiment to compensate for the magnetic north and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? Well, Earth's magnetic field would have interfered with the bar magnet's field and would have given much different results. It would have impacted both the y and x components of the field. And if I were to stick two identical magnets together end to end and run the experiment again, the vectors of the magnetic field would be the same, but the magnitude of the field would be stronger due to the combined magnetic fields of the bar magnets. But the distance to find where B net is equal to 100 Teslas would decrease. Thank you for watching my video.